Welcome to month 3 of the Senior Engineer track at BISTEC Hearts Academy. Last month, we built event-driven microservices with Saga patterns and distributed tracing. This month, we are tackling something that touches every system you'll ever work on: performance. Performance optimization is not about making things fast for the sake of fast. It's about understanding where time goes, making informed trade-offs, and building systems that stay fast as they scale. By the end of this session, you'll know how to profile a real application, identify bottlenecks, fix them, and measure the improvement with hard numbers. Here's how the 4 hours break down. Hour 1 covers profiling fundamentals, setting up APM tools, learning to read flame graphs, and walking through a live profiling demo. Hour 2 is optimization strategies, the optimization hierarchy, database tuning, and caching patterns. Hour 3 is entirely hands-on. You'll work with a deliberately slow application, and your job is to make it fast. Hour 4 is measurement and review, documenting improvements with before and after numbers and presenting the results. The ratio is about 40% theory and 60% hands-on. Everything in the first 2 hours feeds directly into the practical work in hour 3. 5 outcomes for this session. First, you'll know how to use APM tools and profilers to find bottlenecks, not guess at them. Second, you'll understand the optimization hierarchy so you know where to spend your time for maximum impact. Third, you'll implement real caching strategies. Cache aside, read through, write through with proper validation. Fourth, you'll optimize database queries using explained plans and indexing. And fifth, you'll establish performance budgets with percentile-based metrics. These skills are immediately applicable. Every production system has performance problems waiting to be found. Let's start with the tools. There are 5 categories of profiling tools you need to know, and knowing when to reach for each one is as important as knowing how to use them. APM, or Application Performance Monitoring, is your starting point. Azure Application Insights gives you end-to-end distributed tracing, dependency tracking, and automatic anomaly detection out of the box. Datadog and New Relic are strong alternatives, but Application Insights integrates directly with the Azure ecosystem. CPU profiling is next. Flame graphs are the gold standard for understanding where your CPU time goes. Node's built-in ProfLag generates E8 profiles. Chrome DevTools gives you interactive CPU profiling. For production environments, tools like 0x or Clinic generate flame graphs with minimal overhead. Memory profiling uses heap snapshots in Chrome DevTools to show you exactly what's consuming memory. Allocation timelines help you spot leaks, objects that grow over time and never get collected. Database profiling is where I explain analyze becomes your best friend for PostgreSQL. Clean sheet add statements aggregates query statistics across all executions. On Azure Database for PostgreSQL, Query Performance Insight provides this data in a visual dashboard. Frontend profiling rounds out the toolkit. Lighthouse gives you a comprehensive audit. Web Page Test provides real-world multi-location testing. Core Web Vitals are now ranking signals. They matter for SEO and for user experience. The key principle here is critical. Always measure before optimizing. Your intuition about where the bottleneck is. It's wrong more often than it's right. Let the profiler tell you where the time goes. This is the most important concept in the entire session. The optimization hierarchy tells you where to look first, and it will change how you approach every performance problem. Level 1 is architecture. This is where the biggest gains live. Adding a CDN, introducing a caching layer, moving work to asynchronous queues, adding RAID replicas. These are 10x to 1000x improvements. If your architecture is wrong, no amount of code optimization will save you. Level 2 is algorithm. Choosing the right data structure or algorithm can give you 10x to 100x improvement. Switching from an ohm squared nested loop to an ohm log-n sort. Using a hash map instead of scanning an array. Batch processing instead of one at a time. Level 3 is database indexing, query optimization, connection pooling, eliminating n+1 queries. This is 2x to 50x territory. Most web applications spend the majority of their request time in database operations, so this is often where you find the most impactful fixes in practice. Level 4 is caching, Redis, Memcached, HTTP, caching headers, CDN configuration, 2x to 20x improvements. Caching is powerful, but it introduces complexity around invalidation and consistency. Level 5 is called loop optimization, object pooling, lazy loading. 1x to 2x at best. This is where inexperienced developers usually start optimizing, and it's the wrong place to start. The rule is simple: always work top-down. Don't micro-optimize code when your architecture is serving every request from a single database with no caching. Think about this. The last performance issue you fixed, where did it fall on this hierarchy? For most engineers, the answer is levels 3 through 5. But the biggest wins are almost always at levels 1 and 2. Let's dive into level 3, database optimization. For most web applications, this is where the majority of request latency comes from. Starting with diagnosis tools, explain analyze is your first step for any slow query. It shows you the query plan the database chose, the actual execution time, and the buffer usage. You're looking for sequential scans on large tables, nested loops with high row counts, and sorts that spill to disk. Any of these signals points to a missing index or a poorly structured query. pgstat statements is an underrated tool. Enable it and you get automatic tracking of every distinct query, how many times it ran, total execution time, mean time, and standard deviation. Sort by total to find your most expensive queries. Sometimes a query that runs in 5 milliseconds but executes 50,000 times per hour is a bigger problem than a single slow query. A slow query log is your safety net. Set the minimum duration statement threshold to something like 100 milliseconds, and you'll catch any query that takes too long. On Azure Database or PostgreSQL Query Performance Insight gives you this data in a visual dashboard. On the optimization side, indexing is usually your first move. Composite indexes for multi-column where clauses. And remember, column order matters in a composite index. Partial indexes or queries that filter on a constant condition, like active records only, covering indexes to avoid heap lookups entirely. The database can answer the query from the index alone. N+1 queries are the silent killer. Your ARM loads a list of 100 orders, then fires 100 separate queries to load the associated customer for each one. That's 101 queries instead of a single join or 2 queries with an iron clause. If you see the same query pattern repeated dozens of times per request in your query logs, you have an N+1 problem. Connection pooling matters too. The formula for pool size is roughly the number of CPU cores times 2 plus the number of disk spindles. Most applications configure too many connections. 20 to 50 connections is usually enough even for high traffic applications. Use PJ Bouncer for external pooling or your ORM's built-in pool. Finally, query pattern fixes. Stop using select star. Paginate with keyset pagination, not offset. Offset gets slower as the page number increases, because the database still has to count all the skipped rows, and denormalize read-heavy paths when the join cost becomes too high. 4 caching strategies, and each has a specific use case. Cache aside is the most common pattern. Your application checks the cache first. On a miss, it reads from the database, writes the result to the cache, and returns it. The application manages both stores explicitly. This is the default pattern for most read-heavy endpoints. The risk is stale data between TTL expiry and the next write. The mitigation is setting appropriate TTLs and implementing active invalidation whenever the underlying data changes. Read-through is similar, but the cache itself handles loading from the database on a miss. The application only talks to the cache. It never directly queries the database for cache data. CDNs work this way. You request a resource, and the CDN fetches it from the origin server if it doesn't have it cached. This results in simpler application code but gives you less control over the caching behavior. Write-through writes to both the cache and the database synchronously on every write operation. The cache is always consistent with the database. The cost is higher write latency. Every write hits 2 stores. Use this pattern when you cannot tolerate stale reads under any circumstances. Write behind, also called write back, writes to the cache immediately and asynchronously flushes to the database in batches. This gives you the lowest write latency but introduces the risk of data loss if the cache crashes before flushing. Use it for write-heavy workloads where you can tolerate some data loss. Analytics counters, session data, activity logs. For managed caching, Azure Cache for Redis is the recommended service. It supports all 4 patterns, provides built-in replication and clustering, and handles the operational overhead of running Redis yourself. Think about this. For a user profile page that gets 10,000 reads per second but updates once a day, cache aside with a long TTL and active invalidation on profile update is the right choice. For a real-time dashboard showing live order counts right behind makes more sense. Accumulate counts in Redis and flush to the database periodically. You can't improve what you don't measure. Here are the metrics that matter. Starting with Web Vitals and timing. TTFP, or time to first byte, measures your server processing time plus network latency to deliver the first byte of the response. The target is under 200 milliseconds. If your TTFP is high, the problem is on the server side. Look at your database queries, your cache hit rate, and your application logic. FCP, or first contentful paint, is when the user first sees something on screen, text, an image, anything. The target is under 8 seconds. This is affected by render blocking resources, large JavaScript bundles, and server response time. LCP, largest contentful paint, measures when the main content finishes rendering, typically the hero image or the primary text block. The target is under 5 seconds. This is a core web vital and a Google ranking signal. Optimize your hero image, reload critical resources, and eliminate layout shifts to improve LCP. TTI, time to interactive, is when the page is fully responsive to user input. The target is under 8 seconds. Heavy JavaScript execution blocks the main thread and delays interactivity. Code splitting and lazy loading are your primary tools here. Now for percentile latency, and this is crucial. P50 is the median, the typical user experience. Half of all requests are faster than this number. P95 means 1 in 20 users sees this latency or worse. This is usually your SLO target, the number you commit to in your service level objectives. P99 reveals infrastructure issues, garbage collection pauses, cold starts, network timeouts, connection pool exhaustion. And here's the critical insight. Why not averages? Because averages hide outliers. A P50 of 80 milliseconds with a P99 of 12 seconds is a system that looks fine on average, but is terrible for 1% of your users. And if each user makes 100 requests per session, every single user will hit that P99 at least once. Always track percentiles. Always alert on percentile violations. Flame graphs are the most powerful profiling visualization available, and once you learn to read them, you can diagnose performance issues in minutes rather than hours. A flame graph is a stacked bar chart of cold stacks. The x-axis represents time. Wider bars mean more time spent in that function. The y-axis represents stack depth. Each row is a function call in the cold stack. You read them bottom up. The bottom is the entry point to your application, and the top is where time is actually being spent. The workflow has 4 steps. Step 1. Capture a profile. For Node.js, the simplest approach is running your application with a prof flag. This generates a V8 profiling log. Alternatively, attach Chrome DevTools to a running process using the inspect flag. The key is to capture under realistic load. Profiling an idle server tells you nothing useful. Step 2. Generate the flame graph. The 0x tool is excellent for this. Running npx0x against your application generates an interactive flame graph that opens in your browser. Speedscope is another great option that handles multiple profiling formats. Step 3. Analyze the hotspots. Look for wide plateaus at the top of the graph. These are functions consuming significant CPU time. Look for unexpected patterns. If JSON parse is showing up as 40% of your CPU time, that's a signal that you're deserializing too much data or deserializing too frequently. Step 4. Target and fix. Optimize the widest bars first. They represent the most time. Reprofile after each fix to verify the improvement actually materialized. Sometimes fixing one bottleneck reveals the next one hiding behind it. The code snippet at the bottom shows the quick Node.js profiling workflow. Run your app with the prof flag, then process the profiling log. Or use 0x for an interactive flame graph with a single command. Both approaches give you the data you need to make informed optimization decisions. 4 pitfalls to watch out for, and 4 best practices to follow. Premature optimization is the classic mistake. You spend 3 days optimizing a function that accounts for 0.1% of your total request time. Meanwhile, a single database query is taking 800 milliseconds and nobody has looked at it. The fix is simple. Profile first, always. Catching without invalidation is the second pitfall. You add a cache, your reads get fast, and then you spend 2 weeks debugging why users see stale data. Every cache needs a clear invalidation strategy. TTL is the minimum baseline. Active invalidation on writes is better. Think about the invalidation strategy before you implement the cache, not after. Optimizing averages is the third. Your average response time is 220 milliseconds and everything looks green on the dashboard. But your P99 is 8 seconds. 1% of requests are catastrophically slow, and you won't see this if you only look at averages. Track P50, P95, and P99 separately. The N+1 problem is the fourth. Your ORM is silently generating 200 database queries per page load, and you don't even know it. Enable query logging in development and check for repeated query patterns. On the best practices side, measure first and optimize second. Profile in production-like conditions because synthetic benchmarks lie. Set performance budgets and automate them in CI. Fail builds that exceed your LCP or bundle size targets. Track percentiles, not averages. Alert on P95 violations. And focus on the critical path. Background jobs and internal tools can tolerate higher latency, but user-facing hot paths cannot. This is the hands-on challenge. You'll work with a deliberately slow application, and your job is to make it fast. The challenge is divided into 4 areas, each worth 25 points for a total of 100. Profile and diagnose is the first area. Run a profiler on the application. Generate a flame graph. Identify and document the top 3 bottlenecks with specific findings, which function, which query, which metric. Database fixes is the second area. Run explain on the slow queries. Add the missing indexes. Find and fix the N+1 query patterns. The key evidence here is showing the before and after explain output. Caching layer is the third area. Add Redis caching using the cache aside pattern. Set appropriate TTLs based on data freshness requirements. Handle cache invalidation properly on write operations. Measure and report is the fourth area. Compare before and after metrics, response time, throughput, query count. Calculate the percentage improvement. Document what you changed and why each change was necessary. You have 90 minutes for this challenge. The debugging and optimization decisions are yours to make. This section is about turning your optimizations into a professional deliverable. This is what separates a senior engineer from someone who just makes things faster. The ability to communicate the impact clearly. The before and after framework starts with the baseline, the numbers captured before making any changes. QTFP, P95 latency, throughput in requests per second, database query count per request, and memory usage. Then for each optimization, you document what changed, why you chose that approach, what you expected to happen, and what actually happened. Revision guards ensure your performance gains don't disappear next sprint. Add performance test to your CI pipeline. Write how CI runs in GitHub Actions and fails your build if LCP exceeds your budget. Load testing tools like K6 or Artillery can run against staging environments. The goal is to catch regressions before they reach production. Performance budgets are the contracts your team agrees to uphold. For page load, LCP under 2.5 seconds. SCP under 1.8 seconds for API responses. P50 under 100 milliseconds, P95 under 500 milliseconds, P99 under 1 second. For bundle sizes, JavaScript under 200 kilobytes, dzipped. For infrastructure, CPU under 70% at P95 load. These are starting points. Adjust them for your application-specific requirements. When presenting results, use before and after charts with real numbers. A vague statement like response time improved is weak. A specific statement like P95 response time dropped from 3 seconds to 180 milliseconds, a 92% improvement, by adding a composite index on the orders table is what senior engineers deliver. And scoring works on a 4-tier scale. Exceptional is 90 to 100, dramatic, well-documented improvements with thorough profiling evidence. Proficient is 75 to 89, solid optimizations with clear before and after numbers. Developing is 60 to 74, basic optimizations identified, but with incomplete implementation. Beginning is below 60, minimal profiling or optimization effort. The passing score is 75%. The key evaluation criteria focus on evidence, not just code changes. Profiling data, explain output, before and after response times. The optimization without the measurement is incomplete work. Before month 4, there are 6 offline milestones to complete. Set up Azure Application Insights on a personal project for hands-on experience with a real APM tool. Create a Lighthouse CI pipeline and GitHub Actions to automate performance budgets. Implement Redis caching with proper invalidation on a real project, not a toy example. Profile and optimize a real database query using explain analysis. Document a performance budget for your team's application. And write a complete before and after performance improvement report. These milestones are designed to move you from session knowledge to real-world practice. Completing them before month 4 means you arrive ready for the next level of the senior engineer track. Performance is a feature. It's not a nice to have that you address after all the other features are done. It is itself a feature. Users leave slow applications. Search engines penalize slow pages. Slow APIs cascade into slow dependent services of your entire system. The fastest code is the code that never runs. That's the architectural mindset. Can you avoid the work entirely with caching? Can you move it to a background queue? Can you pre-compute the result? From this session, you're taking away 5 concrete skills. Profiling with flame graphs, APM tools, and memory analysis. The optimization hierarchy, always working top-down from architecture to code. Catching strategies with real invalidation patterns. Database tuning with explain plans, proper indexing, and N+1 elimination. And performance budgets with percentile-based monitoring. Complete your offline milestones before month 4. Set up application insights, build that Lighthouse CI pipeline, and implement caching on a real project. The gap between knowing this material and being able to apply it under pressure is bridged only by practice. See you at month 4.